Today's lesson is to understand the difference between a polar covalent bond and a non-polar covalent bond between two atoms. Recall that the definition of a covalent bond was the sharing of electrons between two bonding atoms. However, all covalent bonds are not the same. The two types of covalent bonds are nonpolar and polar. In a nonpolar covalent bond, both atoms equally share the electrons between them. Equally share them. One atom doesn't have more of the electrons than the other. In a polar covalent bond, we have an unequal sharing of electrons between the two bonding atoms. In other words, one of the atoms has more of the electron density of the bond closer to it than the other. This results in a slightly more positive side of the bond and a slightly more negative side of the bond. Only a few molecules are 100% nonpolar, and those are all the diatomic elements. All the diatomic elements have a 100% equal sharing of the electron density between two bonding atoms. Every other molecule has some degree of polar character. It may be very, very small, but there is some degree of polar character. Only when an element is bonded to itself is it truly a 100% nonpolar bond. A question that could be asked now is, we know the difference between an ionic bond and a covalent bond as being the sharing and transfer of electrons, well, ionic being the transfer and covalent being the sharing. And now we've introduced that a polar covalent bond is the unequal sharing of electrons. So we have the equal sharing, unequal sharing, and then transfer. At what point does unequal sharing result in transfer? In other words, as more and more of the electron density resides with one of the atoms in the bond versus the other, at some point, when do we consider that to be fully transferred, right? As the bond becomes more and more polar, when does the polar bond stop being a polar covalent bond and become an ionic bond? And one of the things that we're going to use to help us determine this is the difference in electronegativities between the two bonding atoms. And recall that each element has its own electronegativity value. We determined that from our periodic table chapter. Fluorine being the highest, and with a 4 value, a value of 4, and then francium and cesium being the lowest with 0.6. Everything else is in between. So we are going to use the difference in the electronegativity values between the two bonding atoms as a metric to help us understand whether or not the bond is non-polar covalent, polar covalent, and ionic. And I'll show you how to do that in the next slide. Okay, as mentioned, the delta En value between the two atoms is going to help us understand whether or not the bond character is nonpolar covalent, polar covalent, or ionic. Now, this isn't the only thing that's going to help us understand whether or not a material has ionic bonds or covalent bonds. There are other factors that come into play, and we'll talk about them a little bit later. Now, we have to have a somewhat of an arbitrary boundary between ionic and polar covalent, and also nonpolar and polar covalent. And so we've arbitrarily selected the following values on a continuous scale. So you can see here, let's just look down at our little chart down here, that the difference in electronegativity is going to be a continuous scale. There's no step function. In other words, it's here and then boink, and then here and this. It's continuous. So as the bond gets between more and more electronegativity difference between the two atoms, it increases in its ionic character. But there's no distinct boundaries that you can see on this continuous chart. So we've arbitrarily chosen to be between nonpolar and polar an electronegativity value of 0.4. If it's greater than 0.4, the electronegativity difference between the two atoms, we're going to consider that to be polar. Anything less than that, it's going to be nonpolar. Now, this value here is arbitrary. We can choose it to be 0.3, or we could have chosen it to be 0.2, but generally the upper limit is around 0.4. On the same side, as we go up the ladder to more and more polar, at some level, at some time, it's now going to be a complete transfer of the electron density, and we're going to use that value to be 1.7. All right, when the delta En is 1.7, is greater than 1.7, we're going to consider the bond to be mostly ionic in character. Now, that value, the 1.7, is arbitrarily chosen. I've seen as high as 2.0, I've seen 1.8, I've seen as low as 1.6. But for consistency with your book, we're going to use 1.7. Right? At 1.7, once the value, the delta En, the difference in the electronegativities between the two bonding elements, is greater than 1.7, we're going to say that the bond characteristic is mostly ionic. Everything else in between is going to be considered to be polar. So when we do our calculations and we find out that we just use this chart here, ionic character is greater than 1.7, polar characteristics is less than 1.7, and greater than 0.4, and then anything that equal to or less than 1.7, 0.4 is going to be nonpolar. Right, so here's some examples here. Chlorine, hydrogen chloride is polar covalent, and then sodium chloride is going to be ionic. All right, so let's see how this works. Let's look at our different types of bonds here, and we're going to determine whether or not they have ionic character, polar covalent character, or nonpolar covalent character. So the general approach is determine what two elements are bonded together, determine the electronegativity values for each element. You can use your periodic table or a periodic table of electronegativity values. Subtract the smaller electronegativity value from the larger electronegativity value. Generally, this works out to be that the more metallic element is going to be subtracted from the less metallic element. So if you have two elements together, such as carbon and nitrogen and oxygen, or carbon and oxygen, this is the least metallic element. This is the more metallic element. Even though they're both non-metallics, this one is more towards the left-hand side of the periodic table. So you're going to subtract this value from this value. Then if you get, and then you're going to go to these two things: greater than or equal to 0.4, less than or equal to 0.4, you're going to be nonpolar covalent. Greater than or equal to 1.7, you're going to be ionic. Everything else is going to be polar covalent. So let's see how this works. The first one was very simple. You have two hydrogen atoms, so if you're going to subtract one from the other, you're definitely going to see that this is going to be 0, right? 2.2 minus 2.2 is going to be 0, so that's going to be nonpolar covalent. And we already know that because H2, this is really could be written as H2, that's a diatomic element, and therefore it's nonpolar. Next one is chlorine and hydrogen. So chlorine here, we have 3.16, so let's write that right here, 3.16, and then we're going to subtract from that 2.2. Look on the chart here, 2.2, and that's going to be equal to 0.94. And therefore, that, by definition, is going to be equal to polar covalent. Carbon and hydrogen again. So here's my carbon, here's my hydrogen. again, you're going to subtract hydrogen, which is the lower number from the carbon. So let's do that here. 2.55 minus 2.2, which equals to 0.35. That's a 3. And then, so by definition, since it's less than or equal to 0.4, it's going to be nonpolar, covalent. And the last one, sodium chloride. You got chlorine, which is 3.16, and then you've got sodium, which is 0.9, which is going to be, I believe, 2.26, and therefore that's going to be ionic. It's greater than 1.7. So checks out. So far so good. We've got nonpolar, again because it's diatomic, polar covalent because delta En is greater than 0.4 but less than 1.7. Again, less than 0.4, so it's nonpolar, and then we have ionic. Okay, at this time you're going to try it on your own. So I've given you the electronegativity values of the elements that for here, and I've given you the table to look up once you get your delta En value to determine whether or not it's ionic, polar covalent, or covalent. My suggestion is to put in this column here the electronegativity value of your more electronegative element, which in this case would be these elements here. The lower electronegative value would be here, which would be the more metal type elements here. Get your subtract the two, get your delta En, and then look it up what type of bond type based on that here. So when you're ready to stop the video, copy the information down, work the problem, and then start the video when you're ready to get the answers. So stop the video now. So here are the answers. And I just wanted to show you my way of doing this. Some other folks have a different way of doing this, but I always like to subtract the lower electronegative element value from the higher electronegative element value. So here's my higher electronegative element value. Here's my lower one, so that when I do the math, I'm subtracting this from this to give me a positive value here. So I'm subtracting this from this to get a positive value here. And when you do that, you will see that you sometimes will have to, quote, flip the atoms in the bond, right? The bond here is written as CaO, carbon, nitrogen, hydrogen, fluorine. Generally written so that the element that's further to the left of the periodic table is written first, and the element that's further to the right is written second. So when I flip it around, my larger electronegative element is always going to be the more right on the periodic table. So in this case, it's going to be nitrogen and then carbon. So nitrogen is further right. It's going to be higher electronegative value than carbon. So this subtracted from this would be subtracted from this, etc., etc. And that's why I flipped them over here. So when you do all that, you get these values here, and then these corresponds to these types of bond types. Now you might say, hey, wait a minute. I got different answers for these two values right here. Right? You have polar covalent and ionic, and based on the rules that you gave me, you should have gotten ionic and polar covalent. And that would be 100% correct if the delta En is the only thing that we use to define whether or not a material is ionic or covalent, right? 99% of the time I think it works, but there are a few exceptions. And these are the exceptions. When the delta En is very, very high for two nonmetals bonded together, it's going to be polar covalent. And why is that? Well, even though that this value here is greater than the 1.7 that we've arbitrarily chosen to be our definitive number between polar, covalent, and ionic, it's still two nonmetals bonded together, and there are other things that go into whether or not a material is ionic. First of all, it has to be a solid at room temperature, and HF gas is not. So therefore, by definition, because it doesn't have the right state of matter at room temperature, it can't be ionic. And in this case, this value is lower than what our cutoff value was, which is 1.7. However, it's a nonmetal and metal bonded together. It has a very high melting point and boiling point, so there is a solid at room temperature, and it's also brittle. All characteristics of an ionic solid. Therefore, even though the delta En says it's polar covalent, in truth it's an ionic compound, so it has ionic bonds. Now everything else kind of matches what it should be, right? And this wasn't meant to throw you off or to trick you. It's just to show you that there is some limitations on this method, and you have to be cognizant of other things that go into determining whether or not a bond is covalent, polar covalent, or ionic. So aside from that, if you've gotten all these these values correct, and the other ones here that you mentioned were all good, then I would say that you understand the concept, and you should be able to determine whether or not a bond is polar covalent, ionic, or nonpolar.